Okay, welcome everyone to this continuation of quantum topology. Quantum topology, as usual, is, or not as usual, maybe it's not completely clear, but quantum topology is this idea that you have something that you want to understand, well, in topology, and you have no chance to do that. You have no chance to do that, so you just take it and send it into something that where you have some calculations that you can do, like a linear algebra problem. Yeah, so one of the very sad facts of life that you eventually realize is that the only thing we really understand is how to solve linear equations, and beyond that we have mostly no idea. That's a bit over the top, obviously, but linear algebra really good. Linear algebra problems can still be really hard, but a really hard calculation is still better than you have no idea what to do, right? And it's kind of the idea. So quantum topology is kind of this idea of sending topology problems into algebra. Sometimes people, well, it's the same as with algebraic topology, but kind of here we have more categorical structure going on. So I usually call it linear algebra, but maybe you should call it beefed up linear algebra. You can call it category theory, whatever. It's kind of the same. We'll see. We have a few more details here. But this idea of sending I have no idea calculation into, well, there is a calculation I can do. It might be very tricky, is very standard and one of the main breakthroughs in the history of science. Yeah, I say that again in case it isn't clear. It's still better to have an impossibly difficult calculation than you have no idea what to do anyway. It's still better to have an impossibly complicated calculation. So better send it into linear algebra. Yeah. And I usually I'm very much like, I'm still a very big fan of linear algebra, obviously. But I should admit, there are of course linear algebra problems that are difficult, right? So just because you have a linear algebra problem doesn't mean it's easy. It's just that there are machines to attack that problem. That's kind of the point. And linear algebra problems can still be arbitrarily difficult. Anyway, that was a lot of waffle. So we are wrapping up the topology part, or the category theory part if you want. And then we start with more linear algebra, or we start with linear algebra, or the translation into linear algebra. So not today. Today I just have pictures of Vaughan-Jones, because Vaughan-Jones is fantastic. So a very short history before I give you my definition of what a quantum invariant is. And of course there is Vaughan-Jones here at the National Congress of Mathematicians, 1990. Very happy here, taking the Fields Medal, and yeah, so was a really big breakthrough in the history of science, and it roughly goes as follows. So knot theory started. People were interested in knots for a long time, but as a mass field, it mostly started in the 1920s. And in the 1920s, the only thing we had in topology was algebraic topology. So people used tools from algebraic topology. But algebraic topology is not necessarily very good when it comes to low-dimensional topology. So one of the big problems in the history of topology is that most people are somewhat interested in low-dimensional topology simply because you can imagine it. But most of the tools developed early on are really not all that great for low-dimensional topology. Anyway, so knot theorists first used those invariants, obviously, because that was the toolbox that was around, and they're not that great. And then Jones came around and yay, and changed the subject overnight, and there you go. You get a Fields Medal. Excellent. So you can do that as well. It's one of these Fields Medals where you have this feeling like, oh, I could have done that. That's wrong. I couldn't have done that. I'm not sure about you, but I couldn't have done that. But at least it feels like I could have done it, because the result is actually, Jones' polynomial is fabulous. It's absolutely fabulous. You can explain it to a high school student. Absolutely fabulous. It was still a breakthrough. So in that sense, I could have done it. Obviously, as I said, I couldn't have done it. Anyway, it's great. It's absolutely great. But at the point of discovery, it was still a bit mysterious. It came from very different angles. Very strange thing. I should clarify that here before I show you another picture of Vaughan-Jones. That I don't really believe in hero stories. So, we as humans, we like hero stories. But in science, they're actually not really heroes. So most things are kind of in the air, and then someone is very lucky to discover it. that's just what happens. No one's fault. It's just how it goes, and we all stand on the shoulders of giants. And the point here I want to make is that, oh yes, here's a really good picture of Vaughan Jones. I don't know where I got that from, but there you go. So Vaughan Jones was someone everyone loved. So Vaughan Jones, like one of my heroes, just a perfect human being, not just a really great mathematician, but also a perfect human being. So I give Vaughan Jones here, Jones, the kind of, the spotlight. And yes, you deserve it. Excellent. But again, I don't really believe in hero stories. So, but still, Vaughan Jones was historically the starting point of quantum topology. And then many other people worked on it. And also the way how Vaughan Jones got to the idea was also didn't come out of thin air, obviously, right? We all stand on the shoulders of giants. But I give you the benefit of the doubt if you want, because you were such a great person. And I only met you once. There you go. But everyone talks really good about Vaughan Jones. So Vaughan Jones, really good. Anyway, very soon people realized that these invariants came from categorical structures. That's what we're doing. Like quantum groups who were invented in parallel. That's kind of what I mean. It's kind of in the air, if you want. And all the braided categories, so it's kind of invented in parallel. And the TQFTs, which were kind of invented in parallel, topological quantum field theories. And they all fit together nicely, and that's why we have this story. Yeah. So the point is always categories become a machine for invariants. So this is kind of the point of quantum topology. And essentially it started with Vaughan Jones. But as I said, like now 1,000,005 times, there's a huge bunch of names associated to it. And yeah, we are still in the progress of understanding. So we all stand on the shoulders of giants, but I really don't know where I got this picture from. But while we're doing it, here are more pictures of Vaughan Jones, which sadly died a few years ago. One of the big names in the field. So this is the picture. I'm not sure why this is black and white, and I also don't know where I got the non-black and white picture from. But this was, of course, the picture from before, and I have no clue where I got the other picture from. Yeah, I have really no idea. If someone remembers, have seen it somewhere, let me know. Anyway, so that picture. Anyway, so let's move on. So the whole point that I made in previous videos is essentially the notion, the categorical notion is that of a ribbon category. So a little cobordism here is like a ribbon category. You would need to add crossings, right, to have like knots, but essentially that's the right picture. Kind of a completely categorical object. So a ribbon category is somewhat the correct categorical object. For some slightly silly reasons, like in the last video, I kind of tried to, we see that later coming up, we try to indicate that kind of we want knots, but we actually get ribbons on the algebra side. So let's just go with ribbons, so ribbon category. Right, you have braidings, you have duals, and you have the twist funds. So the twist are those guys. And they're just this input for topology. Yeah. And the point of all of this is, and I call them here numerical invariants, yeah, numerical invariant, linear algebra objects where you could compute something. That's the whole point, right? You want a number, or a polynomial like the Jones polynomial, or maybe a matrix or something like that. Something where you could do something, right? You could fit it in the computer and it can compute the Jones polynomial of a 20 crossing or something like that, right? Instead of just having an abstract problem that you don't know how to solve. And this is like essentially how I would define, I'll do it on the next slide. Just a reminder, the Brouwer category. So Brouwer was the Brouwer was the person, but what I call Brouwer category is like the abstract incarnation of these cobordism categories, right? So that it had by generators and relations. And there was a Brouwer category, whatever. The monoidal, the braided monoidal, pivotal, symmetric, self-dual, Reidemeister one-holes, and then various versions of that, right? It's not symmetric anymore if you have a crossing, so I call that a quantum Brouwer, whatever. And then a quantum invariant, my definition, right? This is my definition of a quantum invariant, and it's not really a definition, it's a pseudo-definition of a quantum invariant. But essentially, the thing we study in quantum topology is somehow a structure-preserving functor from some Brouwer thing to some linear algebra-like category. Yeah? Jones polynomial is in some way or form a functor of that type. and what type of Brouwer category you want is a matter of taste. Maybe you like ribbons, maybe you like knots, maybe you just like plain cobordisms. So you just put whatever kind of favorite symbol in front. Yeah, and it's all like nicely fits together in some graphical calculus. Yeah, so of course then we will have some graphical calculus based in linear algebra as soon as we go here to the right hand side. Right, that's kind of the point. So that's my definition, pseudo definition, whatever you want to call it, of a quantum invariant, which is the central object of quantum topology in some way or form. Yeah? So it tells you something about topology by using linear algebra. That's what it is. And it really tells you something about topology by using graphical linear algebra if you want. Okay? That's essentially what it is. And again, this is not really my definition. It's really just my take. I just repeat it. I already had it here. Right? So there are very various different formulations. People do it slightly differently, and there's, as far as I can tell, not a gold standard definition. But a quantum topology should be a quantum invariant should be a structure preserving functor from some Brouwer thing to a linear algebra like category. That's literally what it is. And we try to make this precise. So I tell you a little bit about linear algebra like categories. Anyway, I hope you enjoyed this video, and I also hope to see you next time.